This is number 34 from Chapter 6, Section 2 in the back of your book. It reads, the overall reaction in commercial heat packs can be represented as 4 Fe in the solid phase reacts with 3 O2 in the gas phase to yield 2 Fe2O3 in the solid phase with a delta H of negative 1,652 kilojoules per mole. A. How much heat is released when 4.00 moles of iron react with excess O2? Now your first inclination might be to simply go 4.00 moles of iron, use a conversion factor, and go and then do your calculations. Moles cancel, 4 times 1,652 kilojoules, and you'll get a value. This is not going to give you the correct value, because for this reaction, it is not 1 mole of iron that is reacting. You see that? You have to have the same... this has to be have a value of 1. And for every 1 mole of iron, you do not get negative 1,652 kilojoules. It's for every 4 moles of iron reacted do you get that amount of heat. So we can't use this setup. We have to go 4.00 moles of iron and then set up our conversion factor. There we are. Now moles of iron will cancel, moles of iron will cancel. My final unit will be in kilojoules, and the question is asking me how much heat is going to be released. I know that is a unit of heat. So now all I have to do is my calculation. So 4.00 times 1652 divided by 4. You can should have been able to see that just by looking at it. But we'll end up with 1652 kilojoules. However, I'd like to point out that I can only use 3 significant figures because of this value here. This value is said to have an infinite number of significant figures because it's an exact value. It's an exact value, not only having 1 significant figure. But I'll use 3 significant figures in my answer, so I have to round to the that 5. Let's see, so I have an answer of 1,650 kilojoules of heat released. Now, some people are going to say, I need to have a negative sign in here and a negative sign in here as a result. The convention with which I was taught was that this negative sign indicates the direction of energy flow. Because this is enthalpy change, this has to indicate the direction of the flow. The question is asking how much heat is released. How much? A magnitude. And in my answer, I say it is 1650 kilojoules released. The presence of this negative sign indicates a direction. This word released indicates a direction. This word release indicates that this reaction is in fact exothermic. The presence of this negative sign indicates the fact that this process is exothermic. So to have both of them at the same time, a negative amount of energy released is kind of like a double negative. So I will not use the negative sign right there. This is the form of the negative sign that I'm using here, just the word released. Move to B. How much heat is released when 1.00 moles of Fe2O3 is produced? So we have 1.00 moles of Fe2O3. And we will set up a conversion factor. Still using 1652 kilojoules, but I need to have moles of Fe2O3 on the bottom so that they can cancel out. And how many moles of Fe2O3 am I involving here? It's for every 2 moles that are being produced according to my according to my balanced chemical equation up here. Get this amount of energy per 2 moles of Fe2O3 produced. So I have to have a 2 on the denominator here. Moles of Fe2O3 will cancel. I'll be left with a unit of kilojoules per mole. And the question is asking me how much heat is released. That's a unit of heat. I know I'm on the right track. So time to get the calculator out. 1 times 1652 divided by 2. Let's see. So I get 826 kilojoules released. Let's see, again, for the same reason, I'm not going to include a negative sign here. This amount of energy is being released. To say that a negative amount of this energy being released would be a double negative. So I'm just going to leave that positive. Let's check my significant figures. See, I have 4 significant figures here. I have 3 significant figures in this 1.00. This 2 is considered to be an exact number. So I need 3 significant figures. That's how many I have. I am done, and that is my answer. We want to see how much heat is released when 1 gram of iron is reacted with excess O2. Now let's remind ourselves this delta H value is a certain amount of heat per mole, per 1 mole. So I can't initially use this 1 gram of iron unless I turn it into a number of moles. So I will start 1.00 grams of iron. Use a conversion factor to move this into moles. Using my periodic table, I know the mass of 1 mole of iron is 55.85 grams. And now I can use that delta H value. Now again, I'm using moles of iron here again. Of iron. And this value for heat is released per how many moles of iron? Per 4 moles of iron. So in this last step, I need to have 4 moles on the bottom. In this situation, grams of iron will cancel, moles of iron will cancel. Now I'll be left with a unit of heat. Question asks how much heat is released. I know I'm on the right track. Now all I have to do is calculate. 1 times 1652 equals divided by 55.8 divided by 4. Let's see, so I have 3 significant figures, 4 significant figures, 4 significant. So I'm going to use 3 significant figures. So according to what I have on my calculator here, I'm going to bring along 7.40. 7.40 kilojoules released. At D, how much heat is released when 10 grams of iron and 2 grams of oxygen are reacted? Now we have a mass of iron and a mass of oxygen. We don't know which one is the limiting reagent. We have to figure out which one's going to run out first, because they're not going to be used at the same rate. According to the balanced chemical equation, for every 4 moles of iron, I need to use 3 moles of oxygen gas. And looking at their molar masses, iron coming in at about 56, oxygen gas coming in at 32 grams per mole. These are going to be very different masses of each of these that I'm going to require in order for this reaction to take place. So even though the coefficients here, the stoichiometric coefficients are pretty similar, 4 to 3, not that far off, the masses of these two substances are going to be very different in terms of what I need. So the first thing I need to do is figure out which one is actually in the limiting reagent. Convert 10 grams of iron into moles of iron. That'll give me, calculator, give me 0.179 moles of iron. 2.00 grams of O2. Convert that into moles of O2. Went in at 32.00 grams O2. Grams of oxygen will cancel. And use sold calculator. 3 significant figures. That's going to come in at 0.0625 moles of O2. Ran out of room a little bit there. So 0.0625 moles of O2. Now, according to my balanced chemical equation, these things need to happen at a 4 to 3 ratio. Okay, so just dividing that out, that ends up being a 1.33 ratio. But when I take my 0.1179 and 0.0625 and find that ratio, I find the ratio is actually closer to 2.86. Okay, in order for this reaction to happen, I need a 1.33 ratio of iron to oxygen. What I have here is a 2.86. The fact that this ratio is larger, indicates that the denominator has gotten smaller. Okay, and so because of that, this having the denominator be not up to snuff, this indicates that the O2 is the limiting factor. So to generate my actual response, I'll take the number of moles of O2, use my enthalpy change there, and this amount of heat is evolved for every 3 moles of oxygen that are used. Put that on the denominator, and now I'm ready to calculate because my moles of oxygen will cancel out and I'll be left with kilojoules, and the question asks how much heat is released. kJ is a unit of heat. So, bust out the calculator. Three significant figures. We'll use 34.4 kilojoules released. Again, the fact that I'm saying the word released kind of gets me out of including that negative sign. If I was not saying released and I was just indicating a heat change, or the direction of the heat change, I would have to include that negative sign to indicate that it was leaving the system and entering the surroundings.